Hello my friends and welcome back to the FUTech HD channel. Production of carbon wire rod at Verona Steelworks. The Verona Steelworks, part of the Pittini Group, is a prime example of how steel tradition meets innovation. The plant is renowned for its high-quality carbon wire rod production, utilized in various applications across the building, construction, and mechanical fields. The production process is planned and controlled, ensuring that the wire rod meets stringent quality standards and environmental certifications. Raw material preparation. The production process begins at the scrapyard, where scrap steel is classified. This classification is crucial to ensure that only suitable materials are used for further processing. Excavators and electromagnets play a vital role in this stage, loading the classified scrap steel into containers. These containers are then transported to the melting furnace, where the scrap steel is melted down. Melting and refining. Once the scrap steel reaches the melting furnace, it undergoes a series of melting and refining processes. The melting furnace at Verona Steelworks is equipped with advanced technology to ensure efficient and thorough melting of the scrap steel. This process transforms the scrap into molten steel, ready for further refinement and casting. Upgraded facilities. Several upgrades have been made to the Verona plant to enhance its production capabilities and environmental performance. The scrapyard coverage has been improved, ensuring better protection of raw materials and more efficient handling. The flue gas system has been upgraded to reduce emissions and improve air quality. Additionally, the billet transfer system has been enhanced to streamline the movement of materials within the plant. Rolling mill. After melting, the molten steel is transferred to the rolling mill, a fully automated facility that represents the pinnacle of modern wire rod production technology. The rolling mill at Verona is renowned for its ability to produce high-quality wire rod with reduced margins, compact packaging, and optimal conveyance. This facility has been significantly upgraded to improve energy efficiency and environmental sustainability, aligning with the Sustainable Steel program launched in 2020. Technological innovation and R&D. The Pittini Group places a strong emphasis on technological innovation and research and development, R&D. Continuous R&D activities and training of collaborators allow the group to produce wire rod with high technological content. This innovation is evident in the controlled hot rolling process at the wire rod mill, which produces a range of high-quality steels. These include extra soft boron steels with high ductility and drawability, as well as high carbon chrome and vanadium steels suitable for producing braided wires and strands. Environmental and quality certifications. Environmental sustainability is a core focus at the Verona Steelworks. The plant has obtained the Environmental Product Declaration (EPD) certification through ICMQ, a quality certification and brand institute for construction products and services. This certification highlights the plant's commitment to environmental protection and sustainable production practices. Quality control is another critical aspect of production at Verona. The products undergo rigorous chemical, mechanical, technological, and microstructural controls in the quality control laboratory. These controls ensure high reliability and compliance with national and international regulations. The HRED Verona's products are certified regarding the percentage of recycled material and adhere to the most sophisticated quality standards. Welcome to the factory, where precision meets industrial strength. Dive into the heart of the production line with this exclusive behind-the-scenes look at how they manufacture top-quality hot-rolled springs. In this video, they take you through the detailed process of hot rolling springs, showcasing the cutting-edge technology and meticulous craftsmanship that goes into every unit produced. From the initial metal rod to the final inspection, experience each step of the dedicated manufacturing process. Hot-rolled spring manufacturing begins with selecting high-quality materials, including carbon steel, stainless steel, and alloy steel. These metals are chosen for their strength, durability, and resistance to deformation under stress. The process starts by heating the metal rods to a high temperature, making them malleable and easy to shape. Once heated, the rods are fed into a series of rolling mills where they are gradually shaped into the desired spring form. The hot rolling process involves passing the metal through pairs of rotating rolls, which reduce the thickness and shape the metal into long, coiled springs. Precision is key during this stage, as consistent thickness and coil dimensions are crucial for the spring's performance. After the initial shaping, the springs undergo a series of secondary processes to enhance their properties. This includes quenching, where the hot springs are rapidly cooled in oil or water baths to increase their hardness. Tempering follows, where the springs are reheated to a lower temperature and then cooled again to relieve internal stresses and improve toughness. Surface finishing is the next step, ensuring the springs are free from any imperfections or surface irregularities. This is typically achieved through processes like shot peening, which involves bombarding the spring surface with small steel balls to improve fatigue resistance. The final step in the manufacturing process is a rigorous inspection to ensure each spring meets the highest quality standards. Advanced testing equipment checks for dimensional accuracy, tensile strength, and overall performance, guaranteeing that every spring delivered is reliable and ready for demanding applications. The 4-roll machine with a linear design is engineered for fabricating XXL monopiles and offshore foundations, specifically designed to handle S460 steel plates used in wind tower structures. This machine is capable of managing plates with a maximum width of 4,200 millimeters and a rolling thickness of up to 180 millimeters. The operation begins with plate feeding, where the steel plate is positioned into the machine. The Human-Machine Interface, HMI, equipped with Siemens CNC technology, facilitates both manual and automated operation, ensuring precision and efficiency. The PGS Ultra-Full CNC system enhances control over the process, providing accurate adjustments and monitoring. During the pre-bending phase, the machine pre-bends the plate edges to minimize flat parts, achieving a maximum pre-bending thickness of 160 millimeters. This step is crucial for ensuring the edges are correctly shaped before the main rolling process. The rolling phase follows, where the machine rolls the plate into the desired cylindrical shape. The machine's fast rotation speed and advanced wireless remote control allow for precise handling and adjustments during rolling, ensuring consistency and quality. The second pre-bending process refines the initial bend, enhancing the roundness and reducing flat parts further. Finally, the machine ejects the formed plate, achieving extremely accurate roundness tolerance and a minimal flat part on the plate. This process ensures the production of high-quality monopiles with exceptional structural integrity. The stand for assembling shells is an essential component in the assembly lines for cylindrical casings, especially for applications like column equipment, wind power towers, and offshore structure supports. This stand is specifically designed for positioning docked shells with precision. Key features include the ability to change the distance between roller blocks using hydraulic cylinders, which ensures flexibility and accuracy during assembly. The hydraulic team series is instrumental in adjusting the weld through left and right movements, providing a stable platform for artificial leveling and welding processes. The assembly process on this stand involves an initial weld, followed by repositioning and subsequent welding to ensure structural integrity. Once a shell section is welded, the stand facilitates the upward movement of the assembly to accommodate the placement of the next workpiece. The position is then adjusted to continue the assembly sequence. This process, supported by hydraulic adjustments and precise positioning, ensures the structural reliability of cylindrical casings used in various heavy-duty applications. The stand's role in enhancing the accuracy and efficiency of the assembly process makes it a vital piece of equipment in the production of large-scale industrial components. The production of electric kettles involves a series of automated and semi-automated processes to ensure high precision, quality, and efficiency. The key stages of the production line are as follows. Nozzle auto blanking and forming. This process involves cutting and shaping the metal sheet to create the nozzle of the kettle. Kettle body auto blanking. Similar to the nozzle, the main body of the kettle is blanked, which means cutting the metal sheet to the required shape and size. Kettle bottom auto blanking. The bottom part of the kettle is cut out from a metal sheet. This step is crucial as the bottom needs to be perfectly shaped to fit with the rest of the kettle body. Inner metal lid auto blanking and forming. The inner lid of the kettle is cut and shaped from a metal sheet. This component requires precision to ensure it fits snugly within the kettle. Inner metal lid edge cutting and hole punching. After forming, the edges of the inner lid are trimmed, and necessary holes are punched to accommodate the kettle's design and functionality. Inner metal lid side hole punching. Additional holes are punched on the sides of the inner lid as required by the design specifications. Sector shape sheet bending. This process involves bending sheets into sector shapes, which are components used in the kettle structure. Kettle body laser welding. The body of the kettle is welded using laser technology, ensuring strong and precise joints. Kettle body forming. The body undergoes forming processes to achieve the desired shape and structure, ready for further assembly. Kettle body top edge cutting and flanging. The top edge of the kettle body is cut and flanged, preparing it for secure assembly with the lid and other components. Kettle body top edge beading. Beading is applied to the top edge to enhance strength and provide a smooth finish. Kettle body edge cutting. Any excess material on the edges of the kettle body is trimmed to achieve a neat finish. Kettle outer body emery grinding. The outer surface of the kettle body is ground using emery to smoothen it and remove any imperfections. Kettle outer body sisal wheel polishing. Sisal wheels are used to polish the outer body, giving it a shiny and smooth finish. Kettle inner body emery grinding. Similar to the outer body, the inner body undergoes emery grinding to ensure a smooth surface. Kettle inner body sisal wheel polishing. The inner body is polished using sisal wheels for a refined finish. Kettle bottom sisal wheel polishing. The bottom part of the kettle is polished using sisal wheels to achieve a high-quality finish. Washing. Remove polishing wax. After polishing, the kettle components are washed to remove any polishing wax residues, ensuring cleanliness and readiness for assembly. Water holes and mark punching. Necessary holes and markings are punched on the kettle body for assembly and functionality. Nozzle welding. The nozzle is welded onto the kettle body, ensuring a secure and leak-proof connection. Kettle spout welding. The spout is welded to the kettle body, a critical step for the pouring functionality of the kettle. Kettle body combined with bottom. The bottom part is assembled with the main body of the kettle, ensuring a tight and secure fit. Kettle spout polishing. The spout undergoes polishing to ensure a smooth and aesthetically pleasing finish. The 76mm tube and 60x60 profile production line begins with the uncoiler, which holds and releases the steel coil. The hold-down roll and coil peeler facilitate the initial feeding of the coil into the line. The pinch leveler flattens the coil and removes any curvature. The skewed conveyor transports the material to the edge miller, which trims the edges for uniformity. In the forming section, the transition and breakdown stands, transition stands, and breakdown stands gradually shape the material. The edge bending stand bends the edges to form a tubular shape, and the cage roll stand further shapes and aligns the tube. In the welding section, the HF welder and squeeze roll stand weld the tube's edges together. The welded tube then enters the cooling section, where air cooling stands and water cooling stands cool the welded seam. Next, The tube passes through the sizing section and cutoff section, where it is resized to precise dimensions and cut to the desired length. The pull-out roll stand assists in maintaining tension and alignment as the tube moves through the line. Finally, the run-out conveyor and coil skid transport and stack the finished tubes for packaging and distribution. The flexible tube production process is a sophisticated and precise method crucial for meeting the ever-increasing demand for metal fabrication services worldwide. Manufacturers continuously seek innovative technology and production solutions to handle a wide array of projects while ensuring reliability and flexibility in their manufacturing processes, all while reducing production costs and lead times. The process begins with the selection of raw materials, typically metal coils, which are uncoiled, straightened, and cut to the required lengths. Quality control measures are crucial at this stage to ensure the material's consistency and suitability for the subsequent steps. Roll forming is a continuous bending operation in which the metal is gradually shaped into a tube through successive sets of rolls. This process ensures the tube's dimensions are consistent and can be customized to specific requirements. The precision and speed of roll forming make it ideal for high-volume production. After roll forming, the edges of the formed tube are welded together to create a continuous seam. Advanced welding techniques, such as laser and TIG, tungsten inert gas welding, are employed to ensure strong, high-quality welds. These methods produce minimal heat-affected zones, preserving the metal's properties and ensuring the tube's structural integrity. Post-welding, the tubes undergo sizing and shaping operations to achieve the final dimensions and tolerances. This step involves passing the tubes through a series of sizing rolls or using hydraulic presses to fine-tune their shape. The tubes are then cut to the desired lengths using high-precision cutting tools. Finishing operations, such as deburring, polishing, and coating, are performed to enhance the tube's surface quality and protect them from corrosion. Throughout the production process, rigorous quality control measures are implemented to ensure the tubes meet stringent industry standards. This includes dimensional inspections, weld integrity tests, and surface quality assessments. The drum cutting and flattening machine operates through a three-stage process to efficiently cut and flatten metal drums, such as mild steel drums. Stage 1. Cutting the top lid. In the first stage, the drum is securely positioned in the machine, and a cutting mechanism, typically a circular saw or shear, is employed to remove the top lid of the drum. The machine ensures precision and stability during the cutting process to avoid deformation. This step often involves automated feeding and clamping systems to hold the drum in place while the cutting tool operates along the drum's circumference, separating the top lid cleanly. Stage 2. Cutting the bottom lid. Following the removal of the top lid, the drum is repositioned, and the same or a similar cutting mechanism is used to cut the bottom lid. This process is similar to the first stage, with the drum securely clamped to maintain stability and precision. The bottom lid is cut and removed, leaving a cylindrical shell of the drum. Stage 3. Cutting the drum from the center and flattening. In the third stage, the cylindrical shell is longitudinally cut into two halves. The drum is positioned horizontally, and a cutting blade or shear runs along the length of the drum, slicing it into two equal halves. After this, the halves are fed into a flattening mechanism. This flattening machine typically consists of a series of rollers or a hydraulic press that applies pressure, gradually flattening the curved drum halves into flat metal sheets. The machine ensures even pressure distribution to achieve a uniform flatness, transforming the curved sections into flat panels suitable for recycling or further processing. The 4000 CNC spring coiling machine is a versatile and advanced piece of equipment designed to handle a wide range of wire diameters, from 1/4 to over 3/4. It offers capabilities for coil diameters up to 10 inches with unlimited feed lengths, and it supports multiple modes of operation, including compression, torsion, and point forming. The machine operates with 6 axes of servo-controlled motion, eliminating the need for mechanical adjustments. The single-point coiling technology allows the 4000 to produce a variety of springs and wire forms. It can handle both right and left-hand coiling by simply changing the chuck. This technology is known for producing higher initial tension rates in extension springs. The machine also features 3D tool movement of the coiling point, providing precise initial tension control and leg bends for torsion springs. The bending arbor facilitates the production of wire forms and torsion springs, potentially eliminating secondary operations. The servo cutter in the 4000 allows for cutting off at the top dead center of the eccentric linkage. This cutter system, adjustable via the DuraBond slide system, offers immense power and precision, capable of cutting high tensile spring steel up to 3/4 in diameter. The DuraBond slide system also ensures high rigidity and a long maintenance-free life. The feed system consists of 2 high-precision gear reducers driven by large servo motors, and it includes 4 sets of 10 inches feed rollers with hydraulic feed roll pressure, providing 50,000 pounds of clamping force per set. This design handles the entire wire range without requiring tooling changes. Dedicated cassette tooling, designed using 3D modeling software, simplifies setup and operation, making the machine user-friendly even for less experienced operators. The W100 CNC is a custom-made hot spring coiling lathe designed for coiling compression springs with wire diameters up to 100 millimeters. These machines are tailored to meet specific customer requirements, handling various wire qualities such as CRC, CRV4, and tungsten. Equipped with servo-controlled CNC technology, the W100 ensures precise and consistent hot coiling processes. It can produce springs with different outer diameters, lengths, and configurations, including tapered bars and cylindrical straight-cut ends. This versatility makes it suitable for various industrial applications requiring high-quality suspension springs.